Welcome to week 6, episode 10. By the way, the quiz number 9, which is pretty long and a bit challenging. So yeah, definitely prepare to work on it maybe a bit earlier. And PA5 is also due. But no worry, PA5 is very straightforward, very simple. All right, so we do have very light amount of assignments due this week by Friday. And the topic for today, emails and P2P, part of P2P. The chances is very high that we need to continue P2P tomorrow. Okay, so let's go ahead and start with email, the system side of it. 2.3, emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got 3 major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about. Let's start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird, I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these 3 major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol. And the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here. The SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got 2 levels of communications in the email application. So this is one between the end users and the local mail server. Okay. Fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, 3 phases, handshaking, and then actual transferring of the emails, and then closing. Opening, closing, the actual transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all three major components together and let me illustrate with the concrete scenario. Alice here is sending an email to Bob over there. Alright, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email. All right, so that's part 1, the system of the email. So now you see the entities involving the communication. Now, let's take a look at the message formats and comments these email server clients are sending to each other. This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, are special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, a command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server will send back to us. And then we could try to type in some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet. Which mail server? Actually Googled up Gmail's mail server. The name is this, SMTP, how appropriate, gmail.com, 425. There we go. IP address being 64 something something. And this is the message coming from the server, 220. Alright, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is. Right, so E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello, and coming from us.edu.tw. How about that? Great, seems to be working. 250. So the server say, ooh, at your service. That's really polite. All right. Then let's try the next comment we saw earlier, mail to. And let's have Gmail sending to pollys email address. How about that? What is this? 530 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport Layer Security Support. I'm guessing this is probably the credential, the public key. So I'm supposed to send back the share secret key with the public key as the key to encrypt. But I don't know how to do that. So yeah, let me try it again then. Playing dumb here. polyhuang@ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from Polly's Gmail address. How about that? No, it keeps bugging me, saying, okay, let's do start TLS. So let's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TLS. All right, so then I suppose I need to send back the, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to telnet to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay. And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, They differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here I meant email. They are similar in this way. Comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails, that comes with an attachment, like a big PDF file after, here is the attachment, if there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I tried to clarify. In SMTP, you see mail from. So this sounds like, following this command, you also tell who the sender is. Receive to, after the comment, after the column, you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange. And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server. In between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol: POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP, being a slightly newer version, it includes a number of other features, including, for example, we could store the email messages in a more structural way. For example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing except that the content is more specifically being emails. And let's take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here, in the authorization phase, server says, okay, I'm ready. Client says, I'm user Bob. So the username there is Bob. Password, being hungry. All right. And server responses with either okay or negative error. It's even more simpler. All right. So okay here, okay here, okay here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So client sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. All right. It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again ends with the period, and only one period in the whole sentence. Right. The client can actually delete an email that has already been read, or in case it's a spam. All right. So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right. So retrieve an email, server sends an email, client delete an email, retrieve another email, server sends another email, and client deletes yet another email. Q and then plus OK, server says goodbye. So that's an example of POP3 exchange. All right, so that was email, the messaging part. Good, and we do have a few questions popping up. So first one is Kevin. Kevin Zhang was asking, is there any email system working in a P2P way? Well, I don't know if any of the popular email services are working in the P2P way. I think most of them are probably working in the client-server way, because people's expectation of the emails is not that real time. Okay, so those who work more like P2P and somewhat functioning like email is these P2P instant messaging or P2P chat systems. Nowadays, we do send text messages, sometimes with the file attachment, with image attachment, and sometimes just send voice. So in a way, these P2P chat is also P2P email, all right? And Gao there asked a follow-up question. Do the peers need to be online simultaneously in order for P2P chat or P2P mail systems to work? Well, normally if you design these P2P chat in a way that it does require peers to be online, yes, because otherwise messages might get lost because the receiver is not there. There's no buffer space to keep the messages. However, one can actually design such a P2P chat more carefully before sending the message out. Check whether the peer is really online. If not online, you can still queue it in the outgoing box. And until the peer that's receiving the message comes back online, then the sender side begins to send the message.
So you see that you need to think a little bit further in order to sustain that there's the message exchange, the chat exchange, or email exchange is going to be reliable there if you work in a P2P form. All right. And yeah, there are a couple questions. Why HELO, not hello, HELLO? Well, I actually don't know, but by going through all these mail server comments, SMTP comment, I did see that coincidentally all the comments are 4-letter. So I'm simply guessing that HELO is just so that to make sure that all the comments are 4 letters. Okay, I don't know if you agree. Yeah, so that was from Hao Yu. Okay, so that's YU or UY. And oh, by the way, thank you, Tim. Yes, ESMTP is extended SMTP. That's great. Thank you. What else? Yeah, that's pretty much all. Now let's move on to a new topic. Now, yeah, you guys are very curious about P2P, right? So good timing. So let's begin talking about P2P. The first part is to talk about the property of doing systems P2P. It's nicely self-scalable. So let's take a look.
P2P applications. To be honest, this is one of my favorite sections in Chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on service, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about 2 applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent. And the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan, from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. And there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting. Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here will need to upload the copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US. And to send N copies altogether, NF over US. And this is the term that we have here. Because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is d mean. Therefore, the download time is f over d mean. The smaller the d mean is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the f over d mean. Now, that's considered an n that's increasing over time, right? Talk about the scalability of the system. The file distribution time, how does it scale with n increasing? Well, this term suggests the overall distribution time will increase linearly in n, okay? While the minimum bandwidth for downlink might not change all that much, okay? So, potentially the overall delay, if we change n, is growing like this. Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Right? Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over D mean, which we explained. And clients overall as aggregated system, okay, must download NF bits, okay, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server, right? So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If you want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, okay, over the entire capacity, entire uplink capacity of the system. Right? So the distribution time bounded by one of these three terms. All right, now consider again if n is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n? Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this. Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time. Right? So the scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, F over U, and let's say that that's 1 hour. And the server uplink rate is 10U, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Right? Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10U. Therefore, what? F over U. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall, all right? And what is the total uplink capacity of the system? So user has 10U. Each client has what? 1U. So 10 of them, also 10U. Altogether, 20U. And how much is this? Half of F over U. And this is what? Half an hour. And is that right? It is right? In P2P's case, 10 users, only half an hour. Okay, so you see the growing trend, linear in client-server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. And this is the big advantage of running an internet service in the P2P architecture over the client-server architecture. There. That is P2P. What's nice about P2P? Now let's quickly take a closer look at an example, the BitTorrent. First example is BitTorrent. The way the file is distributed in BitTorrent is instead of sending one big file at a time, it's divided into smaller chunks. 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. Okay? So BitTorrent. Now, there's one more entity. It's called tracker. So this machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first, contact the tracker and then tracker in return, giving Alice a list of the peers. And this is the initial set of peers that Alice will connect to. Now, once Alice is connected to the torrent, then Alice can try to explore other peers and then re-establish connections to these other peers. So, tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, yeah, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. And Alice at the beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of the exchange. That could be a bit disturbing. There's a special term for it called a churn. Hopefully there's less amount of these churns, but sometimes it's not really controllable. And at the end,
All right, we're back. Yeah, so that video playing was not very smooth. Let's see what I can do here. Yeah, why don't I try to address the questions? Because we are actually almost till the end of the lecture. All right, so Tian, Tian there was asking, why does the library ban P2P traffic? Well, there's a very simple reason for that. They would not like that the library computers, the resource being occupied for storing files that you guys pull down from the internet. Because as a result, other users on the internet might be querying for these files that you downloaded. And as a result, the library machines might be busy uploading files. That could be occupying the resources provided by the library. All right, so let's see Kevin's question. In the previous example, do we assume an user can upload part of the file before it has received the whole file? Yes, that is the whole idea. Once you get a particular chunk, you are free to allow other people to download this chunk. Yeah, so it's also the same idea is very much like the pipelining. If you recall, back in chapter 1, we could send a huge file at one time from one router to the next router. And the next router can wait until receiving the huge file before start sending to the next router. But that is going to be a long way just to receive the whole file before transmitting. So there, internet as a message passing design, we cut the big files into smaller packets. So here, similarly, in P2P, what we're downloading or sharing are large files, generally speaking. So cut them into smaller chunks is exactly to boost the performance. So the whole point is so that we can start sharing early, dividing them into chunks. And Rocket, I would guess security. Yeah, that's one of the concern the library staff has. But I would say that's less than issue, but more that the resources being occupied. If security is the main concern, they probably should block all the involuntary downloads from users, because we download things that are really having some what is that? Spywares on it. Yeah. So nowadays it's easy that you download things coming with the spyware, right? Yeah. So students, whether the staff members should really trust students. I am more willing, but I'm pretty sure that some of the staff members they want to make sure that there's little work as possible. Yeah. And I think the whole NTU bans P2P. I think for many P2P apps, if they use a port number that's well known, okay, and not changing it over time, it's easy to ban them. So if you want to avoid your P2P app that you design later in life being banned easily, just hop your ports. That would actually prevent a means from blocking your traffic easily. I think Ben and Rocket were having a discussion there. So, and by the way, Jiazi, thank you for letting me know NTU blocks. Actually, NTU's policy is very strict, just so that you know. It's very hard to communicate with them, because my lab does quite a bit of these traffic monitoring and traffic probing network measurement projects. I sometimes have students sending a large number of UDP packets out, and we get calls all the time from the computing center of NTU. It's not very easy to communicate with them. So I would try to be understanding, because they might not know very well what is the implication of having some UDP traffic, having certain traffic coming from P2P apps. They are all very occupied, very busy. Let me just say it that way. Okay. I missed Tim and Rocket's message is around 12:01 and 12:02. All right. So, hey, you guys, help me fill it in. You see on the video that I have this, buffering sign because that's the time the OBS upload is not working well. So I quickly stop the stream and then restart. Stop the stream and restart the stream. That somehow hack the problem away. I've been reading posts on OBS. So this version of OBS and Catalina is just not working very well. And I just don't have the time to downgrade my Mac OS back to Mojave. So yeah, occasionally we have this issue, but it's okay. Then we start the Q&A early, and we will push the quiz to tomorrow. All right. And let me see, Darius. I suppose it's either Torren. Yeah. Oh, good. So Darius is there helping in answering the questions. Pei An. Let's see. So is there an algorithm behind to optimize P2P sharing efficiency? That is a very good question. Well, I think 10 years ago, I did have a group of students investigating how you optimize the sharing experience, sharing efficiency. It actually has a lot to do with the interconnectivity of the P2P network. So the rule of thumb is to make sure that you bootstrap the newcomers such that the P2P network is balancedly connected as possible, so that you avoid having these rare chunks being left out. Okay, I know. Yeah, sometimes. So some of the slides talking about requesting chunks, you guys didn't hear. I will definitely replay those back tomorrow. I know that you guys are very curious about P2P apps, so we'll do it again tomorrow. So let's call it a day today, and tune in tomorrow. Okay, ciao. I'm gonna leave the stream for just a little bit longer, so in case you have further questions you want to ask. If not, feel free to go. All right, have lunch. Okay, good. So I'm just gonna end the stream and I'll see you tomorrow.